We're going to take chapter 12, chemical kinetics, and use a review document, the second version. I've got some highlighted, and we're going to run through these unless you come up with something that is particularly bothersome, and we'll digress to that. All right. Start at the top. Number one. If the reaction is first order in hydrogen peroxide, and this is the reaction they're working from, where this is, that looks like a catalyzed reaction. But no, conditions must be modified so that it only produces the triiodide. This is not the decomposition of hydrogen peroxide. I thought it was in the beginning. But it's first order in H2O2. So that means if we were to write the rate law, it would be some K and then H2O2, and that would be first order. But we have two other reactants here that have to be considered. All right. So, and H plus, it tells us, does it tell us? Oh, yeah. Second order in the iodide and zero order in the H plus. Okay. Which of the following rate laws would be preferred? All right. We keep this one, keep that one. That one goes out because it's equal to 1. Right. So the preferred form is this, K times just these two factors. And that would be E. Trick question. All right. 2. A reaction has the rate law, let's see, ABC squared, rate A, B, and C. There you go. As that rate law, what is the overall order? Oh, overall order is just the sum. Right? This is the order for A, order for B, order for C. Overall was 5. Okay, let's see. We'll get another one like that in a minute. We'll skip down 4. If the reaction 2HI yields H2 and I2, correct? Yep. Is second order, which of the following will yield a linear plot? Oh, if it's second order in, and when it just says second order, it doesn't say what, usually means reactant. Second order in that reactant. Then the linear plot, if we plotted this, let's see, it's second order. So if we plotted, let's see, time. If we just plotted concentration of I and its second order, we'd get a curve like that. If we did the natural log, we'd still get another curve. But if we did the inverse, we get straight line. That's for second order. So B should be the answer. Okay, let's see. Oh, 5 is all by itself. I was looking below That doesn't go with 5. Which of the following statements about enzymes is incorrect? Okay. Let's see. All are correct is the bottom. All right, how about the first one? We're looking for the incorrect one. Enzymes, usually proteins that catalyze specific biological reactions. Yes, that's true. Most of them, the vast majority, are proteins. So that's why we say usually proteins. They're equal to inorganic catalysts in inefficiency. No. They're actually more efficient by several orders of magnitude. In fact, inorganic catalysts, well, can work at any temperature, but many of them, you have to get the temperature very high for them to work. But that's a false one. Several thousand are now known. Yeah, probably more than that. Molecules they react with are called substrates. Yeah, we didn't cover that in class, but oh yeah, I think I did mention that. The reactants upon which the enzyme acts, called substrates. Very often there's just one substrate, but there can be. Well, actually, I can think of reactions where there are at least 2 substrates. So we found our false one. That was B. All right. Skipping down to 8. The definition. A free radical is a chemical species that what? Has an unpaired electron. Paired electrons tend to be less reactive. If you have a species with all the electrons are paired, it's not a free radical. If you have one where one electron is unpaired, then you have a free radical. So that's D. And free radicals can be neutral or they can be charged. Either way, they can be very small. In fact, they can be single atoms or they can be big molecules. It only requires an unpaired electron. Okay, number 9. The rate expression for a particular reaction is AB squared. Okay. Need K first, huh? Constant. And A and B squared, was it? Yeah. Okay. If the initial concentration of B, okay, is increased from 0.1 to 0.4. So in one experiment, we have 0.1. And then the next one we have 0.4. Okay. The initial rate will increase by which of the following factors? Well, if we increase this one by what factor? Times 4, right? Okay. And the effect that it has on the overall reaction is squared. So it'd be 16 times would increase the initial rate. Oh, while we're here, what if we say, what if we do the same thing for A? Right, times 4. Well, the effect that A would have on the rate would just be times 4. But the overall rate would be 4 times 16. 64 times. If you did it to both of them. All right. D. 10. Read the answer. D. The answer to D is 10. For which order reaction is the half-life of the reaction proportional to 1 over K? talking about half-life. 10 half-life equals, well, let's see, zero order, first order, second order. My memory is not that good. So let's go to useful information. Zero order half-life is A/2K. Yep. So this would be, let's move this out here. T1.5 equals A/2K, right? The next one I think is 0.693 over K. I believe. Yeah. And then the last one is 1 over K times A0. 1 over K times A0. Okay. So to answer the question, all of them. They're all proportional to 1 over K. You just say that. They're all proportional to 1 over K. Right. Number 13. Of the following, we're talking about molecularity here. Which type of collision is most likely to be the rate determining step in a proposed mechanism? If we have all possible elementary steps in our mechanism, then we would choose one of these as the most limiting, the one that would run the slowest. And that depends on the probability of the collisions occurring. Right? Unimolecular, I mean, you only need one molecule, so all you need is any other molecule that slams into it and gives it enough energy, doesn't matter what its orientation is, would cause a unimolecular to go. Bimolecular, you have to have enough energy, and then two of them have to approach with the correct orientation, so it would be less likely. Termolecular, you've got to have three molecules coming together with the amount of energy they need, plus proper orientation for all three of them. And then non-molecular is just a filler. There's no such thing. Termolecular would be the correct one because it's the least likely. If it's there in your mechanism, it will run the slowest. There's no argument with that. All right, number 14. See this reaction. Here we got the decomposition. H2O2 yields 2 waters. This is the overall reaction. Has the following mechanism. Okay, so we've got these two steps that are that enter into this reaction. So the first step, we take one of these, H2O2. And by the way, when we write an overall reaction, if there's anything that's not, it may participate in the reaction, but it's not consumed by the reaction, or if it's an additional piece of information, we usually put it here on the arrow. Right? So it looks like iodide is going to be part of that. And the mechanism says the first thing it does is it reacts with the iodide ion. And it produces water plus this ion. Then we take the other one and it reacts with this species and produces another water. So we got the two waters here and oxygen plus that. Okay. So the question is, which is the catalyst? Remember the definition of a catalyst. It comes in at the beginning, goes out at the end. It looks like nothing ever happened to it, right? That's this one right here. Okay, that's the catalyst. What about this one? Right? Because if we add these together, that disappears and this disappears. But this is not the catalyst, right? That's an intermediate. Yep. All right. Let's see. Okay. Now we're going to get method of initial rates. 17. I'm going to put that way up here. We've got plenty of room. Okay. If we have, if we're using initial rates, we're only interested in the reactants. So we have MnO4 minus as a reactant. Let's put it about right here. MnO4 minus. And oxalic acid. I think that's what that is. 2C2O4. And then hydrogen. Okay. And then the rate. I'm going to put the rate over here because the way we write the rate law is the rate comes first, right? So I'm going to put the rate over here. Okay, the question is, what's the order of the rate law with respect to this one? So if we write the rate law like this, we're going to have, excuse me, constant. We're going to have MnO4 minus to the N order. Then we're going to have H2C2O4 to the M order. And then we're going to have H plus to the P order. Okay. So I might have to, well, I'll just move down here. Okay. So if we need to find something out about the MnO4, we want that one to be the one that varies between two of our experiments. Right? So we could have the first one and then one of the other three. But the other condition is that these two have to remain constant. So if we use the first one and the second one, these are constant, and this one varies. Then we can ratio, let's see, if we say rate for, and I want to put the second one on top. So I'm going to say 2 times, let's see, 8 times 10 to the minus 4 is the rate. 8 times 10 to the minus 4 is the rate here for the first one. And then we'll stretch this across here. So 8 times 10 to the minus 4 would give us K, and 2 times 10 to the minus 3. And then K on the bottom would be 2 times 10 to the minus 4. 2 times 10 to the minus 4. And then this concentration would be 1 times 10 to the minus 3. And this both would be to the N power. And then I could write the others in, but the top and the bottom ones are going to be the same for these two, and the same for these two. So they go out anyway. And the K cancels out. So that leaves us an equation in one unknown. There. So this reaction, this divided into that is 4, correct? Okay. And this is 2 to the N power. So N would have to be 2, wouldn't it? We'd have to square 2, so N equals 2. And that would be C. We could do the same thing with each of the others, find out what they are. And then once we found out what the orders are for each one, then we can find out what K is. So how would you find out what K was? Take any one of the experiments, plug in your orders, plug in the rate for that experiment, and then solve it for K. Well, the rate and the concentrations. Plug in these values, that value, solve for K. Then you've got the complete rate law. But that's a little much to do for an exam. So I limit it to just one. Okay, let's see. 18. The rate law for this reaction is second order NO and first order O2. What happens to the rate when the concentration of O2 is triple? We just did one like this, didn't we? All right, if we have NO squared and O2, oops. Well, if we triple O2, we triple the rate because it's to the first power. Right. Okay, we'll come to an energy diagram again in a minute. I've got a couple of them in here. Scroll. Here, let's do this one. 24. What fraction of a reactant remains after 5 half-lives of a first order reaction? All right, what's the definition of a half-life? The time it takes for half of the original to disappear. Okay. It doesn't matter if it's first order or zero order or second order. That's fluff. That's extra information you don't need. So if you say your original amount is X, then after one half-life, after one half-life, you have half of that, right? So you have 1/2 of X. If you do another one, then you have half of that. So half of a half is a fourth, right? We can just keep doing that 5 times, right? 1, 2, 3, 4, 5. So the next one would be half of that would be 1 to the 8x, and this would be 1 to the 16x, and this would be 1 to the 32nd x. So 1/32 would be 5 half-lives. Or if you like mathematics, it's 1/2 to the n, however many times. So n is 5, 2 to the 5th is 32. Okay, let's see, 25. Okay, the following question refers to this reaction. 2A2 and B2. 2A2 plus B2 yields 2C. Okay. And we have a mechanism proposed. The first step is fast. Which step is rate? Oh, I don't need to put all that on the board. The rate determining step is the slowest one, right? All right, so that'd be step 2. Okay. How about 26? Let's see, for a reaction the little a, big A equals products. A0 is 6.4, and the first two half-lives are 60 and 30. If this reaction is known to be zero order, what's K? Okay. Right. I like to bring everything out and put it in a form that I recognize. If we have A0, the initial concentration is 6.4. Right, so we're starting out at 6.4 molar. And first two half-lives. The first half-life is 60 minutes. So this will be time. And the first half-life, of course, this is zero time. First half-life is 60 minutes. And that means we would have 3.2 molar at that point. The second half-life is 30 minutes. So after 30 more minutes, or a total of 90, we would have half of that, which would be what? 1.6. Is that right?
Yeah.
Yeah, 1.6. Molar. Okay, that's what we're given. The reaction is known to be zero order. Okay. If we have zero order, what is the expression for half-life? We did that a little earlier. I think it's over A over 2K, is it? Yeah. Okay. All right. So K without units. All right. So we can pick any one of those. Right? If we know initial, if the half-life of the first one is 60 minutes, since we don't need units, I'm not going to put them in there. And A0 is 6.4, then 2 times K. Right, so we just bring K over here and 60 over there. So K equals 6.4 divided by 120. I can do that one in my head. So that's 5.33 times 10. Actually, it's only 5.3. Two significant figures there. Minus 2. I think it was 3 significant figures. Whoever wrote this problem wasn't paying attention to their significant figures. But that's the closest answer. Okay. We should be able to, if we did it with this one, get the same answer. All right, that's 26. '27 is referencing all that garbage above the question, I think. Isn't it? This following mechanism has been. No. Yes. Yes, it is. Okay, 27. So what's the question? According to collision theory, the activated complex that forms in step 1 would have which of the following structures? Dotted lines represent partial bonds. Okay, so if we start off with step 1, we're going to have A and some bond with A. We don't know if it's a single or a doublet. It doesn't really matter. And then we have B with this bond. And when they collide, they have enough energy. They're going to move into this situation where these bonds are breaking. We represent those by dashed lines. Oops. I'm creating. And so the only other possibility is to start forming bonds here. Okay. That's as far as we can go, right? For the collision, to proceed and reach an intermediate step, this activated complex, that's as far as we can go. So that would be B. And the way this is an artifact of Word. This image up here is related to that choice right there. So this choice is that image. And the lines are really faint. There are dotted lines right in here. Can you barely see them? Yeah. So that's what it should look like. It's plainer here than it is up there. And it's a lot better back there too. I think that's a problem with the projector. It's old.
See the dotted line that you pointed.
Yeah. Every once in a while, I'll tell somebody in management, they need to get rid of these projectors, put a big screen up front. Okay, next one, let's see. Oh, so there's repetition there. Let's get down to 31. The rate constant for a reaction at two different temperatures are given below. What's the activation energy? All right. This means that we're going to have to find the Arrhenius equation that gives us two temperatures and two rate constants are involved. And that's far right hand on your useful information, far right hand side, bottom. So that's the natural log of K2 over K1. K2 over K1 equals, notice I don't have this memorized, E sub A over R. That's the activation energy. This is the gas constant. And then this is 1 over, is it T2 first or T1 first? T1 minus 1 over T2. So that's your Arrhenius equation for finding the activation energy if you know temperatures and rate constants. But actually, it's like any other equation. If you know all the variables except for one, you can solve for it. So if we knew this one, of course, that's a constant. We knew this one, this one, this one, this one, and say this one, then we know what this one is, or vice versa. But in this case, the initial temperature, T1, is 30 degrees. So this is 30. Let's do it like this. Just fill in things. 1 over 30 plus 273, because it has to be in K. The second temperature is 49. 49 plus 273. And over here, we're solving for activation energy. Okay, so this is our unknown. And this one is 8.3142, I think. Is that right? Or 3145, excuse me. 5. Go. And that's joules per gram, joules per mole K. And over here, we have natural log of the K2 is associated with this temperature, 1.21 times 10 to the minus 3. And then the first temperature, K, is 1.38, 10 to the minus 4. There we go. So that's our equation that requires solution. Do this side first. 1.21 exponent minus 1.38 exponent 4. Divide. So this part right here, I got just in case I make a mistake, we'll come back and figure it out. 7, 7. That's it. So then the natural log of that value is right here. This is 2.1711. This side, I'm going to resolve this one first. So that's the inverse of 303, right? Inverse of 303, and then the inverse of 322. Yeah, take the inverse of that. Inverse, where's my inverse? There it is. And subtract that one from this one. And this term in here is 1.947 times 10 to the minus 4. Okay. So this is in the numerator. This is in the denominator. So I divide this one into that one. 8.3145. And those two terms together are 2.342 times 10 to the minus 5. Okay. So this term resolved puts that in the numerator. I bring it over here into the denominator. And that's equal to the activation energy. Let's see. Yep. Just about. Okay, this is going to be 9.2697 times 10 to the 4th joules per mole. Probably in kilojoules. Yep. Okay, so kilojoules we would take that and say, take 10 to the 3rd out of that. Right, like that. 9.2697. And this then would become kilojoules. And then what's left over is 10 times this one, which would be 92.7 kilojoules per mole. Okay. All right. All right, next. 32. Consider the following balanced reaction and the experimental results that follow. Okay. Let's see, 2NO. Yes. Plus 2H2. It has to be a gas also, although it's not written. N2 gas. And 2H2O. That's a gas. This must be an exothermic reaction. Okay. What are the rate law orders for NO and H2? All right, we should be able to do this one fairly quick. We write the rate law over here in its generic form, so to speak. This would be NO to the N order and H2 to the M order. Okay, so we'll set up, let's see. Yeah, let's do NO first. We want NO to vary and H2 to be constant. So that would be the first and the third, right? The first and the third experiment. So the rate for the third experiment is 2.4. 2.4 equals K. Let's see. And then the concentration of NO for the third one is 0.02, no, excuse me, 0.3, 0.3, 03. to the N. And we've set it up so that this is going to cancel. Right, the H2 is going to cancel because it's the same on the top and the bottom. And K will cancel. And the first experiment is 0.6, right? 0.6. 0. And its concentration, the NO concentration for that one is 0.015. To the N. So 0.6 into 2.4 is 4, right? Okay. And this would be 2 to the N. So N equals 2. Makes this one 2. Now we can say, all right, if we're going to let the H2 vary, but the NO stay the same, that would be 1 and 2. So that's 1.20. And now this is going to be the same, top and bottom. This one is going to vary. H2 for the 1.20, 0.04. And the first one is 0.6. 0. And the hydrogen concentration for that one is 0.02. Oh. So we get here is 2. And this is 2 to the N. So N has to be equal to 1, right? Okay, so that's 1. Now, it just wants the rate law orders for NO and H2 in that order. NOH2 would be 2 and 1. See. At this point, we could find out what K is. All we have to do is take any one of the experiments, plug these values in, and find K. Right. 33. Yeah, 33. Get up some. Get both of them. 33. The first order decomposition of H2O2 at minus 28 degrees occurs with a half-life of 50 seconds. Okay. So let's put what we know. First order decomposition of H2O2. So H2O2 rate equals K times H2O2 to the first order. Okay. The answer here has a time factor in it. So which one of the versions do we need? The differential or the integrated? We need the integrated version. So the integrated version, our useful information has it up there, almost to the top on the right. Let's see. A equals minus KT. No, that's zero order. First order is natural log minus KT. So the natural log of H2 minus KT plus natural log of H2O2 initial. That's the equation we want. So what do we need to find out? Well, the initial concentration was given, right? 25.2. This is 25.2 molar. The time elapsed is 50 seconds. Right? 50 seconds, that's given. That's given. This is going to be our answer right here. We need to find out what K is. So can we do that? Oh, wait a minute. Hold on a second. No, this is half-life. We're looking for 5 minutes, right? 5 minutes. 50 seconds is the first half-life. Yep. First half-life is 50 seconds. If we start with a concentration of 25.2, right, 25.2, and we start at 0 time, concentration of H2O2, start there, then after 50 seconds, is it? Yeah, 50 seconds, we have half of that. Let's see, 1, 2, 6, right? Okay. So we've got this, we're going to find that, we need that. So what's the half-life formula for first order? 0.693 over 2K, isn't it? And 3. No, it's just K. Just K. Okay. All right, we know the half-life is 50 seconds. 0.693. In fact, we don't need to know the initial concentration of this. Then that's our K. So K is going to be 0.693 divided by 50. Okay. That'll give us K. Which is 1.386 times 10 to the minus 2. I'm going to keep decimal points for rounding error. Okay, so now we have this value here. Log of H2O2 that has minus, and this is 1.386 times 10 to the minus 2. T. This is in seconds. This uses seconds, right? So this needs to be converted to seconds. How many seconds is 5 minutes? You're right, yeah. 300. 300 seconds. Okay, and then plus the natural log of our initial concentration. So if we're going for 5 minutes, we're starting with 25.2. 25.2. There we go. So now we should be able to solve that. Let's see, what's the natural log of 25.2? Let's see here. There it is. 3.2268. 3.2268. And then this term, let me flip that around and multiply by 300. This is minus 4.158 and plus that value. Okay, so this natural log of H2O2 is equal to this minus and that plus. So let's see, change that sign and put them together. So this is minus 0.93115. So how do we get this from that? Remember the definition of logarithms? Natural logarithms base E. So this value is that power of E. Okay, so I got that in my calculator already. All I have to do now is hit the E to the X. This is E to the X. And that's H2O2 concentration after 300 seconds is 0.394 molar. Yep. Okie dokie. Right, who's next? 34. For the second order reaction, nitrogen monoxide plus ozone yields nitrogen dioxide plus oxygen. The rate constant has been measured to be this value at 298, and the activation energy has been measured at 311.4 over the temperature range of 195 to 304. What's the rate constant at 233? Okay, so this is the Arrhenius equation, but with a different unknown, right? And let's see, how much of this can I remember? So the rate equation is natural log K2 over K1 is equal to E sub A, yeah, E sub A over R in 1 and 2 over R. And 1, 2. There you go. There's our integrated Arrhenius equation. Now, what do we know? What are we given? The rate constant has been measured to be 1.08 times 10 to the 7th at 298. And then which way are we going? Down. So I would think that we could call 1 the higher temperature and 195 the lower temperature, but it really doesn't matter. As long as we get the rate constants associated with the proper temperature. So we could use the lower temperature here and the higher temperature there. Let's see if it works. Let's see. Rate constant for 233. So we're going to call this one our higher temperature. And the rate constant for the lower temperature is, let's see, where is it? Lower temperature. Wait a minute. Hold on a second. Am I going at this wrong? Rate constant at 1 temperature. Activation energy. Okay. Okay. Yeah, it only gives us 1 rate constant at the higher temperature, 108 times 10 to the 7th. So the higher temperature would be yeah, I got it backwards. The higher temperature is the K2, and the K1 is the one we're looking for. Okay, so that's 1.8 times 10 to the 7th is this one. 1.08 times 10 to the 7th. Activation energy was 11.4 kilojoules. All right, this is in joules per mole K. So we have to change 11.4 to joules. So I'd say 11.4 times 10 to the 3rd joules. Because you can plug that number into your calculator and it'll be perfectly happy. You don't have to convert it to scientific notation. Okay, so this was K2. That means this is the higher temperature. The higher temperature is 298, right? 298, right? That's what that should be. Yep, 298. So this is, and the K is already given. So this is 298. And this one is the lower temperature, which is 233. Here we go. Now, that should be set up correctly. All right, I'm gonna do these first. Take the inverse of 233. And then take the inverse of 298 and subtract it from the previous one. So this would be 9.3614 times 10 to the minus 4. And then I'm going to do that term, 11.4 with an exponent of 3 and 8.3145 divided. And this term is 1.3711 times 10 to the third. Then I multiply those two together. And that gives me 1.2835. Okay, and that's equal to this term, right? How do we separate those two? All right, that's another log identity. When you have the log of A divided by B, that's the same thing as the log of A minus the log of B. Remember that? Okay, so this one would be the natural log of 1.08 times 10 to the 7th minus the natural log of K1. Okay, so let's resolve that one. 1.08 exponent 7. See if that's the right. Yes, 7. And take the natural log of that. And this is 16.195 minus natural log of K1 equals 1.2835. So if I take this one over here, it becomes negative 16.195. And that will be 2 minus. That's minus log K1 equals minus 14.912. So get rid of the negatives, right? Negatives, positive. Now we can say K1 is equal to E to the 14.912. There it is. So rounding error. I got a little rounding error in there. I got K1 equals 2.99 times 10 to the 6th. So the closest one is probably a rounding error. I kept all my decimals as we were going. And that answer was probably calculated with intermittent rounding. That's one that makes sense. So the best answer is C. Yeah, the trick to these guys is be very methodical about your calculations. That's why I opted to do intermediates, sections, and then put them together. It'll be easier to find the error if I did it that way. Okay, let's see. Who's next? We'll skip a few. Aha, here we go. Okay, I tell you what, let's make it smaller. Won't let me do it this way. There we go. All right, 39, 40, and 41. So I can get 39 and 40 in there. Are based upon that energy diagram. So the reaction coordinate, that is the progress of the reactions from left to right, energy of all the components is on the left. So the first 39 says, which letter shows the activation energy without use of a catalyst. So it would be the red line or the blue line. Red line. Without a catalyst takes more energy. So we would follow to the peak and we say, all right, what's the difference between where we started with reactants and where we end at the top of the red? That's E. All right, see E over there? E stretches from the top of that peak to the energy of the reactants. So that's E. All right. 40 says, which letter shows activation with catalyst? We just moved down to the blue line because catalysts always reduce the activation energy magnitude. So that would be A, from reactants to the top of the B, to the top of the blue line. That would be A. Oh, I don't have the answer in there. How'd that happen? There it is. That's strange. Well, not really when you consider it's Acrobat. Okay, the last one, which letter shows the activation energy for the reverse reaction without the catalyst? So the reverse reaction, we'd start with products and we go from that energy level to the top of the red line. And that's C. Takes that much energy to go backwards. All right. Yeah, we're going to look at this one. Let's see. What's the value of the rate constant? Okay. Using this graph above, answer the following two questions. Okay. All right. So we're going to 42 and 43. 42 wants us to use this graph. This is an Arrhenius plot. And remember the straight line for the Arrhenius plot is log K minus V spade over R. Log K minus V spade over R times 1 over T plus log of that times 1 over T plus log A, right? Yeah, okay. So this is our straight line representation, and we just need 2 or more Ks at different temperatures to make that plot. All right, we have, hold on a second. Well, I'm looking at the right one. No, I don't think I am. No, I'm not looking at the right one. You know why? Because I'm not thinking. This is, all right. This is the integrated rate law for this reaction. The integrated rate law, if we have a straight line with natural log against time, that's first order, right? Raw data would be 0 order, inverse would be second order. So this is first order reaction. That means the first order reaction is the natural log of the concentration. Yeah, at any given time equals K time plus the natural log of the initial concentration. There we go. I think that's right. No, it's a negative slope. So this has to be minus. There we go. Yep. Okay. So now that I got the right equation, what's the question? What's the order of this reaction? Oh, well, the order has to be first order. right? First order. 43. Based upon that same, what's the value of the rate constant K? Right? This term right here, minus K, actually, the slope of that line, let's go back up. Slope of that line is what? The slope is minus 2.20 times 10 to the minus 5. 2.20 times 10 to the minus 5. All right, that's the slope. And X is time. So if minus K times time is this, then this minus K, this is K, positive value. 2.2 times 10 to the minus 5. Now, if I'd been sneaky, I would have changed one of those to minus 2.2 times 10 to the minus 5 to catch you with that distinction between these two. Right? That minus before there goes away if you want to find out what K is. Is that, oh, that's the last one. Now, is there any one of these that we haven't covered that you want to talk about? Or does this have you mastered kinetics already? Yeah.
You went over it, but can you cover the potential energy diagram, like the rest of what the answers would be?
What number is that?
Just like 39, 40, 41.
Oh, yeah. Okay. Yeah. Okay. So if we have a diagram like this, this is just reaction progress. It could be time, usually is something related to time. It just shows the reaction proceeding from reactants to products. And for this particular reaction, we have reactants are at higher energy than the products. So the products are at this level of energy, and the reactants are at this level of energy. There's your energy. Okay, so we're following along, and these reactants, if they have enough energy, and they can, we can be adding energy as they go also. We can add energy to this reaction. Maybe this is not enough energy for the reaction to proceed. Or remember the energy or the temperature measurement of a mixture is related to the average kinetic energy of all the members of the mixture. So what that means is some of them are at this level of energy lower, some are here, most of them are here, and then some of them are out here. Well, the ones that are out here are the ones that have enough energy to go. So if we add energy to it, we're going to shift that curve to give us more. So if we drew a separate curve there, this would be energy level, and this would be numbers of reactants. Right, so some of them have a little bit of energy here, and most of them have this level, and then you sort of tail off. And you need this much energy for the reaction to go. So it's only a small number of them that have enough energy. Right? If we increase the temperature, then we shift that curve over, and we sort of do like this. So that gives us more. So if we do that, then we're giving these things energy, and the ones that have enough energy, when they collide, they reach this point, which is the activated complex. That's one way of expressing it. I'll just leave it at that. So this is where we're beginning to break bonds we need to break bonds with the reactants and start to form bonds for the products. But we're not there yet. we need just a little bit of nudge to go over this side. And if we make it over this side, then we go down to products. So this is the hurdle. We need that much activation energy. To make it over to products. Now, like I said here, only some of them will have enough energy to do that. Okay, so that's uncatalyzed. If we introduce a catalyst, then the catalyst participates in the reaction in such a way that it reduces the amount of energy required to get over that hump. So it goes down here. Okay, the beginning energy of the reactants and the final energy doesn't change. But since we reduce the activation energy, that means more of our reactants have sufficient energy to make it over the hump. It's a different hump. Now, the difference in the activation here would be like this is activation energy for the catalyzed reaction, a lot lower. And the reaction will proceed faster. From last semester, we want to know the enthalpy of that reaction. That's the difference here. So the enthalpy didn't change either.